Hey, Piers, C-Car here. I just want to clarify a couple things about electric forces and how they relate to gravitational forces and maybe some differences in the way we'll approach them. The first thing that I want to bring up is you notice that the way I have the electric force written out here, I use absolute value symbols. And the reason why I want to focus with Coulomb's law on absolute values is I think it's going to help us avoid making a bunch of silly mistakes. I would hope, remember with gravity that we always had a negative sign. We multiply negative gravitational constant times the product of the masses divided by how far apart squared. And that negative sign turned out to be valuable in terms of telling us that the vector force is always in the opposite direction of a radius vector. And that's a way of telling us that that force is an attractive force. And as far as we know, gravity always is attractive. With electricity, we sometimes have attractive forces, sometimes repulsive forces. And I think the positive and negative signs there can make us think something other than what they're really telling us. We'll see that in context in just a couple minutes. Well, when we do the vector math, a positive value for the force would mean pushing apart, and a negative value would mean attracting. But I'm going to just use reasoning skills. Hey, these are the same signs, so they're pushing apart. Or, hey, these are opposite signs, so they're pulling together to make my decisions about direction of force. So I'm just going to do the math to find amounts of force. That's why I've got everything sitting in absolute value signs. But Coulomb's law, it really is just like gravity in the sense of take some constant to make us get units that we like, multiply it by whatever property of matter it is that makes these things do that force to each other, multiply the product of them, divide by how far apart they are square, their inverse square laws. And so in that sense, the structure of Coulomb's law or Newton's law of gravity really are the same. But anyway, oh, and we're using Q's, of course, for quantity of charge, although we just call it charge now, but the origin of the Q is quantity of charge, coulombs being our unit. Now, the gravitational constant, big G, 6.67 times 10 to the negative 11, that's a really tiny number. That was MKS units, by the way, what I just said. Likewise, we've got, for MKS units, we've got an electric constant, which is 9 times 10 to the 9. That is rounded slightly. You can look up a more exact value, but it's really, really close. If you're doing 2 digits, it's 9. So 9 times 10 to the 9, that's 9 billion. So that electric constant is way, way, way bigger than the gravitational constant. And it's going to turn out that electric forces are way larger amounts than gravitational forces. We'll work that out in just a minute. Another thing that you might have picked up on as being weird when you read about this in your textbook is this idea here of replacing that electric constant K with this 1 over 4 pi epsilon naught thing. And epsilon naught is just some electric constant, just like the K is. And a reasonable person would look at that and say, why would any sane person ever do that? That just looks more complicated. Since 1 divided by 4 pi epsilon naught is exactly the same thing as K, then I don't see why anybody would ever bother to choose to use it. And that's reasonable thinking. And over the course of the next few weeks, I think it'll unfold for us. Why would anyone do that? So just be patient with it. And when you see 1 over 4 pi epsilon naught, just know that the value of that is 9 times 10 to the 9 Newton meters squared over Coulomb squared. So yay for that. It is important. You can see what I wrote here about Coulomb's law only being valid for point charges. That is actually going to matter for us because you can imagine, unlike with gravity, where because of the way that they form, most very large objects, planets, stars, move on, they all tend to be roughly spherical in shape because of the way that they formed. But this really isn't true for charging things. I could charge a teacup or I could charge, it needs a saucer, I could charge a teacup if I really felt like it, or I could charge a meter stick, and I can certainly make all kinds of different shapes to what's the charge distribution like that aren't spherical. And so it really is going to matter that Coulomb's law only works for point charges. We'll see in the near future what to do when I don't have a point charge. But if you want to use Coulomb's law, well, you're dealing with point charges. If you don't have point charges, then you're not just doing Coulomb's law. Although we can, just like with Earth, we don't treat, when we're dealing with the gravitational pull of Earth on something, we don't worry about Earth's size and shape. Isaac Newton did the proof of that you can treat it as though it's all that mass located at the center. You could treat, when you're outside of the Earth, you could treat the whole thing like a point mass. Likewise, if we're outside a spherical charge, then we can treat it like it's just a point charge, all located right at the center. So, convenient. Now, I do want us to look at gravity versus electricity. I've already worked out these numbers because it would take way too long for you to sit here and watch a video of me doing the calculations. But let's take a hydrogen atom. One electron, one proton, some distance apart. And on average, they're 5 times 10 to the negative 11 meters apart. Wow, that's tiny. And you can see here the elementary charge. Elementary charge, we know that the electron and the proton have the same amount of charge, just opposite signs. So put a negative sign in front of that for an electron, put a positive sign in front for a proton, although again, when I'm calculating forces, I'm just going to be looking at amounts anyhow. And you can see here that I've got the masses of electrons and protons. Something I notice right away, if I'm thinking about comparing what's the electric force versus what's the gravitational force between the electron and proton in that atom, is that the masses, in MKS units, the masses are much smaller numbers than the charges. And just, comparing amounts, hey, I'm only using MKS units. I mean, it's not like you could reasonably compare 1 Coulomb versus 1 kilogram. But we're going to get much tinier numbers using those masses, is my point. And also the constant, that K, is a way bigger number for electricity than the one for gravity, big G. And so I can anticipate, just looking at these numbers, that I'm going to get way larger numbers for electricity, electrical forces, than for gravitational forces. And of course, we remember always to square the denominator. And to calculate the gravitational force, then we end up getting this really, really, really tiny number, which I hope I didn't make a mistake on. You'll catch it if I did. Now we compare that really, really, really tiny number with the same calculation, but for electricity. And remember, I'm just using here, I'm just using positive values for both charges because I just want an amount. And so yes, I could, for these two charges, I could have just written that elementary charge squared. I didn't this time, but in the future I certainly will. So multiplying all those out, I get, and again, same distance apart, I get a way bigger number for the gravitational force than I do for the electric force. Sorry, I said that backwards. I get a way bigger number for the electric force. And just saying bigger, of course, doesn't really even do it justice. If I look at a ratio of these two numbers, then wow, I even drew an enormous exclamation point because wow. The ratio of those, 2 times 10 to the 39, I can't even conceive of how big that, a billion is 10 to the 9. So a billion is 10 to the 18, and a billions is 10 to the 27, and we're still not even getting anywhere near the difference between those numbers. So electricity beats gravity like all the time. Although here's a fun question then. If electricity is so much stronger than gravity, then why is the large-scale structure of the universe so much more so about gravity than it is about electricity? I'll let you think about that one a little bit. And you can ask me about it later if you care to. Anyway, I want to quickly do a little sample piece of math. by the way, in case you can't see, the charge on the far left is a value of negative 3q. The charge at the origin is a charge of negative q, just in case you can't read that on your screen. And the one at the origin then is the lower right blue charge. And I'm always using, you can expect if you aren't sure, it is a safe assumption if you see me using blue, I'm probably trying to represent a negative charge, and I'll use the color red for a positive charge. Now, if I want to find the net force on this blue negative Q charge at the origin, a mistake that I noticed a lot of people doing in the past when we were doing this kind of thing with gravitational forces is that a lot of people were making the mistake of trying to find some kind of, do a sum of the charges pulling that thing. You know, we want to know about, hey, what are the forces on this charge right here? And people then were taking like averages of all the other masses when we were dealing with gravity, or finding sums of all those other masses, and then like, okay, so it's like there's some mass right here and it's pulling on that thing this way, and that did not work for you then and it will not work for you now. The thing that we're trying to do a summation of is the forces. We're not summing up masses, we're adding up the forces. And the forces that we're dealing with here, there is an electric force from this charge on the left, this negative 3q charge, and there is a force from this positive q charge above, and each of those two things applies a force. Now I can calculate amounts and I can figure out direction, and let's first think about direction just with our brains. I'll look at the y-axis first. So if I think about forces on this charge from the charge up above, then let's see, they're opposite charges, so that's an attractive force. So I know that there will be a force along the y-axis towards the other charge. And when I think about forces from the negative charge over to the left of it, well then, since those are the same kind of charge, it's going to be a repulsive force pushing away. And so what direction is away from the thing on the left? When I look at forces on this charge, away would be to the right. Now, before I draw that, I'm thinking about how long should I make that arrow? And the length that I'm going to make that arrow is, well, it's a bigger charge, so that would lead to a bigger amount of force, but it's also further away, which would lead to a smaller amount of force. And knowing that it's an inverse square, I also know that this 2, that part's going to get squared, so I'll have a 4 in the denominator with a 3 in the numerator, so it's actually going to be a little bit of a smaller force. So I'll have an arrow that way, and that's about to disappear there. So finding the net force in component form, well, let's look at, first let's just look at the y-axis. I think that'll be the easier one. So the force on the y-axis, I'm just doing big K, I'm just doing the K constant times the product of the absolute values. So I'm just doing times charge. They're both a charge of capital Q. One's positive, one's negative, but again, not paying attention to the sign. So I'm just looking at the absolute value there and dividing by that distance squared. So the y-axis force is K times Q is just Q squared over D squared. And now thinking about direction, I know that that force is up. That's on the positive Y. So there, now I even have a vector statement about that. So here's the first part of my answer. Second part of my answer, looking at the x-axis, I've got K times the first charge times the second charge, just like with gravity, it really doesn't matter what order, and dividing by that distance squared. Now I'm squaring 2d, so when I calculate that, then I get 3kq squared in my numerator and 4d d squared for a denominator. And thinking about the direction then, that's to the right, that's along the positive x-axis. So I hat gives me a vector statement, and there we go. So to answer the question of, hey, what's the net force in component form? Well, I just need to add those two together. So my answer really is just going to be as straightforward as three kq squared over 4d squared in the x direction, I hat, plus 1 kq squared over d squared j hat. So there's my answer for version A of answering that. Now, I like giving answers in component form, but sometimes I actually need to know an amount. And component form doesn't tell me an amount, it just tells me the components along each axis. So if I did need that, then I need to do some vector math. So I've got an arrow going this way, and I'm adding to it an arrow going this way, and the arrow going to the right is 3/4 times all that stuff, and the arrow going on the y-axis is 1 times all that stuff, and I need the resultant of that. I don't know why I drew it so small, because I've got plenty of space here, but never mind. I'm just going to redraw that real quick. So I've got 1 unit going on the y-axis and 3/4 of that on the x-axis. Looking for that black arrow then is our resultant. I need to know this angle. And so I do 1 squared plus 3/4 squared. 3/4 squared is 9/16 plus 16/16 gives me the total of that would be 25/16. Take the square root, and I get 5/4. Oh, actually, that's a 3, 4, 5 right triangle, knowing that 1 is also 4/4. It's a 3, 4, 5 right triangle. So the amount of the force is 5/4. Now I'll add back in all that other stuff that I left off. And the direction, inverse tangent of 3/4 over 1, or inverse tangent of 3/4. You could also just recognize that, since that is a 3, 4, 5 triangle, 37 degrees. That would be a 37 degrees angle to the right of the y-axis, or the more traditional way of expressing that angle would be to measure this angle. So you could also say that's 5/4 kq squared over d squared at a 53-degree angle above the x-axis. And anyway, there we're done. So the important thing to take away is we're doing a summation of forces. We do an individual force calculation for each of these charges that is pushing or pulling this charge that we're interested in. And so then we find, oh, there was a net force going that way, and that was our answer. We could do it in component or magnitude and direction form, and I think I'm done. I'll talk to you later.